For a long time in civil engineering, mainly two materials were used: steel and concrete. Steel used in buildings, in offshore structures, in bridges, tanks, transmission lines, in sheetings, and storm surge barriers. The other material, concrete, reinforced or pre-stressed, is also to be found in buildings, in offshore structures, in bridges, or, for example, silos. Steel has advantages: high allowable stresses and a relatively light weight. Steel has a highly controllable quality and can be cut to tight tolerances. And steel structures are rapidly erected. But there are disadvantages as well. The basic costs of steel structures may be more expensive. Fire protection may be required, and painting to inhibit corrosion may be necessary. Concrete has advantages as well. Compared to steel structures, it can be cheaper. If well made, there are only few corrosion problems. And concrete is the ideal material to withstand compression stress. Concrete can be easily poured into various shapes on site, or concrete elements can be prefabricated. However, concrete is massive and so heavier. Shrinkage and creep may occur, and the behavior of concrete is non-linear. Shrinkage, due to chemical reactions, occurs mainly in the first 28 days after solidification. Shrinkage and expansion due to temperature is the same for concrete and steel and is always happening. The Münchner model is used for a simplified explanation of shrinkage. Concrete is a porous material. Humidity has an important effect. The distance between the fiber-like particles of the mortar depends mainly on humidity. Reduction of humidity leads to shrinkage. Differences in humidity in the cross-section lead to tension near the surface and then to cracks. Creep is the increasing deformation due to loading as a function of time. A concentrated load on a beam generates an elastic deformation alpha and a deformation due to creep beta changing with time. Beta has a delayed elastic component and a plastic component. Creep occurs predominantly in places with high stresses. Cracks in the fiber-like particles allow some displacement, followed by a recovery by new bonds. Is steel or concrete the most economical solution? Or could a combination of the materials offer the greatest benefits? This is the idea behind composite structures. A composite structure is basically a combination of a steel frame and a concrete topping, connected by shear connectors. The steel frame mainly carries the tensile forces, the concrete the compressive forces, and at the same time may serve as a floor. In this diagram, two separate beams, one on top of the other, are considered. Each beam carries 50% of the load acting upon them. The maximum stress is sigma. But when the two beams are interconnected with shear connectors, the same load now produces a maximum stress of only 0.5 sigma. The beam deflection is also considerably reduced. The lower beam is in tension. Obviously, steel is the best material here. The concrete slab is in compression. Reinforced or pre-stressed concrete is clearly more suitable. The shear connectors ensure the full composite action between the two materials. Several types of shear connectors have been designed. The headed stud is the most common. It is attached to a beam by stud welding. Due to its circular symmetry, the connector is not affected by the direction of the shear forces. Per man per day, about 400 studs can be mounted, which makes the headed stud also the most economical type of connector. Before considering developments in shear connectors, the load deflection diagram. In a construction, first the steel structure is erected, and then the concrete slab is poured. The steel structure carries its own weight, plus the dead load of the just poured concrete. So far, shear connectors are not effective. Solidification of the concrete creates the composite structure, now effective for live load only. Deflection, due to increasing live load, follows curve A. Another possibility: a construction propped during pouring of the concrete slab. After solidification of the concrete, the props are removed and steel and concrete cooperate in carrying dead and live loads. Deflection due to the dead load and increasing live load follows curve B. In the ultimate situation, the deformation and load carrying capacity are the same for both propped and unpropped methods. The main difference lies in the total deflection in service conditions. By using a method without props, the deflection will be alpha. In using props, it will be beta. Another essential point is the shear connector behavior. If, due to its compact shape, a connector suffers no deformation up to the ultimate load, and supposing no concrete crushing occurs, full connection is established. The slender-headed studs, however, are prone to deformation. Even more so when the concrete starts crushing at the stud footing. It means a redistribution of shear forces over the other connectors. Consequently, a partial connection is established. A new development is a headed stud with a thicker footing. A 16mm stud, because of its thicker footing, will behave like a 20mm stud. Another development is a strip with holes, the perfo bond strip, welded to the top flange over the full length. If the strip is welded automatically, this can be an attractive alternative. Mechanically, the concrete can here be considered to act as a shear connector in lateral direction. The Hilti shear connector is nailed to the steel flange. It can be installed in all weather conditions. Rain and frost have no effect on the quality of the connection. In this structure, timber formwork is necessary for the concrete slab poured in situ. But timber formwork is wasteful of material, expensive, and labor-intensive. Several alternatives have thus been developed. Formwork consisting of profiled steel deck. Formwork of reinforced concrete plates. And completely pre-cast concrete deck plates. Profiled steel deck. To improve the bond between the steel plate and the concrete, dimples or similar embossments are rolled into the plate. In this case, the reinforcement is applied to improve fire resistance. Dimples to improve the bond between steel and concrete, and headed studs. For passing a cross girder, the steel formwork can be simply supported by the girder. Holes in the formwork are a method to cross a beam continuously. Another solution for this continuous crossing is through-deck stud welding. The studs are welded to the beams through the steel deck. Instead of a steel deck, reinforced concrete plates may be used as a formwork. Finally, it is possible to place completely pre-cast deck plates. By requiring the plates to be made long before application, creep and shrinkage can be reduced considerably. In the concrete plates, pockets are made to fit around the studs. Pockets and gaps are filled with non-shrinking grout. In a beam, the space between the flanges is filled with concrete, which improves the local and overall stability of the steel section. Reinforcement also improves the load carrying capacity and fire resistance. If, due to fire, the steel flanges lose load carrying capacity, a redistribution of stresses takes place. The reinforcement, situated in the cooler region, takes over. For columns, three solutions are common. Firstly, concrete encased steel columns. The concrete covering is made after erection of the steel structure and consequently requires formwork. In case of fire, the load carrying capacity is hardly affected. The second solution is a prefabricated column with reinforced concrete filling between the flanges only. The third solution is a hollow section, a tube, filled with reinforced concrete. Here, the steel surface is fully exposed to an eventual fire. In many situations, concrete-filled steel tubes form an attractive solution. The reinforcement helps to maintain the fire resistance integrity. This beneficial effect can be demonstrated by a computer analysis. It offers an excellent simulation of the heat distribution in a cross-section, here consisting of an I section with concrete and reinforcement. With intervals of 15 minutes, the heat distribution is shown. In the light blue areas, the temperature is still normal. The white regions are load-carrying, though affected by the heat. Clearly, the reinforcement and web remain in the heat-protected area. Therefore, HP sections are used with relatively thick webs. Several solutions for beam-to-column connections are available. A hinged connection. After mounting the beam-to-column connection, when the floor is made, the remaining space is filled with concrete. And an alternative. A connection transmitting a bending moment. The basic ideas are that the connection is made to meet the strength requirements and is covered with concrete to meet the fire resistance requirements. Practice has proved that composite structures offer a highly cost-effective solution in many situations.